Okay, welcome back to Mr. Hassan's Maths channel. This is question number 6 from the January 2020 International A-Level Pure Mathematics P3 Edexcel paper. And this is a question here about absolute value functions, modulus functions. Here we're given a graph of a function with the equation y equals fx, where f of x is equal to 2. F of x is equal to 2 times the modulus. So f of x is equal to 2 times the modulus of 2x minus 1 and then plus 3. F of x is equal to 2 times the modulus of 2x minus 5 plus 3. And part A tells us that the vertex of the graph is at point P as shown. State the coordinates of P. Okay, so there's many different ways of doing this. Actually, you can find the coordinates of P in different ways. You can use transformations of the fact that you can take the original function, which is y, the parent function, which is y equals a modulus of x, and think about the transformations of the vertex and how it end up at that point. So what that point would be according to this transformation. Okay, so you can think of this as y equals 2 times, and you got like inside the function it's got 2x minus 5 plus 3. So you think about what transformations take place from here to there. Okay, so this is the original function y equals f of x. What are the transformations that take place, take you from there to there? So you could talk about the horizontal transformations first, and then the vertical transformations, and you can end up with P where it's supposed to be. Okay, that's probably maybe kind of complicated for this one. You could also think about in terms of working out the coordinates of P in terms of working out what the equation of this part of the graph is, and working out what the equation of that part of the graph is, and seeing where they intersect. That's the second option. A third option, which is probably the easiest option in this case, is to have a look at the equation of the graph, which is f of x equals 2 times the modulus of 2x minus 5 plus 3, and treat it very similarly to when we've completed the square in quadratics, because when we complete the square we basically end up with an expression which is squared, meaning that expression will always be either positive or 0. Okay, they'll either be positive or 0 because it's got squared. Now, in a similar fashion, this part of this expression here will always be positive. Okay, so once you have substitute any value of x in here, the modulus of whatever you find is going to make it become a positive value. Then you multiply that positive value by 2 and add 3. Okay, so the modulus of 2x minus 5 is always going to be greater than or equal to 0, always. Okay, because you're going to end up having to find its modulus, so it's going to, if it's negative, it's going to become positive. So the lowest value this can ever have, is when the modulus of 2x minus 5 is equal to 0. And it's equal to 0 when basically what's inside it becomes 0. So when 2x minus 5 is 0, so when x equals 5 over 2. Okay, so the coordinates of P for the x value is going to be 2.5. And the y value, well, when this whole thing becomes 0, you're going to have 2 times 0 plus 3. So this part of it leaves you with the y coordinate of P. Okay, so that's by far the easiest way of working out the coordinates of this point, which is a minimum point. It's basically the minimum point on this graph, the lowest it can ever reach. The lowest it can ever reach is when this thing here becomes 0, which is 2 times 0 plus 3, which is 3. And the x value which causes this to become 0 is when x equals 5 over 2, because 2x minus 5 equals 0 when x equals 5 over 2. Just rearranging and solving that equation. So that's by far the easiest way of finding the coordinates of P. I mean, if we did it by transformations, it will still work. I'm going to show you all the different ways of doing it just to give a more complete idea of your understanding. So if I do it in terms of transformations, now the first thing that's happening here, the first thing we're going to deal with, if we're thinking about the original function as being the modulus of x, and we've come to here. So we start off with the vertex in this position here. We start off with the vertex like this. Okay, that's the original shape. Let me just group this together as one. Okay, so that's how we start off, something like that. We can make it a bit bigger. All right, so we start off with something like this. It should be a bit more shallower than that, actually, according to... Can I make it shallower than that? I don't think I can change it now. Because it shouldn't be parallel to this, because this has got a more steeper gradient. But let me make it... Whoops, what have I done there? Deleted the whole page instead. Okay, so what I'm going to do is I'm going to make it a bit more shallow than this, because it doesn't have the same gradient as this. It has a shallower gradient than that, so I have to draw it with a different gradient, a shallower gradient. Okay, so this is the something that's supposed to be the original. Group it together. Okay, so this is y equals the modulus of x. Now the first thing that's happened to it are the first thing you deal with are the things that are inside the function. Now inside the function is what's inside here, the 2x minus 5. And when we're dealing with transformations, we always deal with what's inside the function, and we start with the things which are in the order opposite of BIDMAS, because inside the function always acts a bit weird. All right, so you start with the we're going to start with the this part here, the minus 5. Okay, so fx minus 5. Fx minus 5. If I just think about fx minus 5, that means translation of 5, 0. You go 5 in the x direction. So this is going to end up somewhere over here at 5. Okay, so that's the first thing that happens. And then we deal with the f2x. Now that means a horizontal stretch of factor a half, stretch of factor of a half, because it's inside the function, it's opposite, so it's horizontal, it's inside the function, and you stretch with a factor of a half. So all the x values are going to be halved. All the x values are going to be halved. So now it's going to have the shape, the same gradient as this, and this x value is going to move here, okay, but the shape of the graph is going to get narrower. So now it's going to have the same gradient as this curve, so I can draw it with the same gradient as this curve, okay, but it's going to be going like this from this point. It's going to look like this, and it's going to look like this. So the x values have been halved. Okay, so let me just get rid of that part here. Okay, so this is now going to be 2.5. Okay, but it's going to be 0. Okay, so that we've dealt with what's inside the function. So also, the gradient of this graph at the moment is going to be, it's going to be 2. So it's going to get even, so if it's still going to be not the same gradient as this, it's still going to be like this. Still going to be like this. It's not as shallow as before, but less shallow than this. So the gradient of this graph is going to be 2, because the x values have been halved, right? So everything has been stretched, okay, horizontally. So basically, what's going to happen here is before it was stretched, okay, this would have been 5. That would have gone to 5. Now the whole thing has moved this way, but that would have stayed as 5. Because that would have been, so that would have been 5. So this is going to stay as 5. So at this moment, this is 5 here. okay, and this is 2.5. All right, because when it was stretched originally, okay, then that point would have stayed as it is. See, this whole thing would have moved. Everything would have got closer to this, so it would have gone from it being like this. Okay, so it would have been even shallower. So before this is what it looked like. So this is quite a long-winded way of doing it, but I'm just explaining to you. So it would have looked like this before we just stretched it now. The original would have been like that. This point would have stayed where it is because it's on the y-axis. So when you stretch this horizontally, it doesn't change. But all these points get halved. The distance from the x-axis get halved. So this is 5, it becomes 2.5. Okay, so that's why it's become stretched. You know, that point stayed where it was, and you know that stayed as 5, and everything else, you know, got stretched, got closer. So that's why it's got a bit more. The gradient is now a bit tight, a bit more steep. Okay, so let me just get rid of this. Okay, so that's what it looks like up to this point. And then the next thing that happens is the other things that are outside the function. Like you have y equals 2 times f of x. That means you multiply all the y coordinates by 2. Okay, so then this gets multiplied by 2, so it goes to 10. This stays where it is. So basically the gradient now becomes the same as the gradient of this graph. Okay, because the gradient is now the same as the gradient of that graph. It will have exactly the same gradient as that graph, so it will be parallel to that side and parallel on this side. Okay, so everything gets stretched by a factor of 2. What's on the x-axis doesn't change, okay, but it's a vertical stretch of factor 2. So anything on the x-axis doesn't change, but anything away from the x-axis, its y-coordinate is multiplied by 2. So that 5 becomes now a 10. Okay, so it cuts the y-axis now at 10. Okay, and then finally what happens is it gets moved up by 3 units. It gets moved up by 3 units. It's a vertical translation of 3. So this goes up to there and to there. So you end up at 2.53. So that's a very long-winded way of doing it. Okay, using transformations. It's far easier to do it in the way that I mentioned here, where you can think about it in terms of almost like completing the square. In the same way we think of in finding the vertex and completing the square. It's almost the same kind of concept. All right, so now that's that method. So I'll also teach you a further method, just for understanding's sake. Okay, and that method is as follows. What I will do is I'll say, okay, one of these is the positive part of the graph, and one of these is the negative argument. The positive argument is when you leave it as it is. So you got y equals 2 times 2x minus 5 plus 3. This is the positive argument of the graph. So that's going to be y equals 4x minus 10 plus 3. Okay, so you're going to have y equals 4x minus 7. So that's obviously this part of the graph, the one with the positive gradient. Y equals 4x minus 7 is this part of the graph. And then you got the negative part of the graph where y equals 2 times, and you just switch the sign of what's inside here. So it's going to be minus 2x and plus 5 and plus 3. That's going to be the negative argument. That's going to give you y equals minus 4x plus 10 plus 3. Okay, and that's going to give us y equals minus 4x plus 13. Okay, which is this part of the graph. This is y equals negative 4x plus 13. And we can see what we mentioned before, that it was first going to go through at 5 as originally, and then it was stretched by a factor of a half, so it went to here, and then it was stretched by a factor of 2 vertically, so it went to 10 first, and then it was raised by 3 units. So this 10 would have been gone up to 13, as we can see from here. This is minus 4x plus 13, so it fits in with what we drew earlier. Okay, so the y-intercept there is 13. Okay, now what we can do here is we can find out where these two lines intersect, which will be at P. So if I say minus 4x plus 13 is equal to 4x minus 7, I'll end up with 13 plus 7, which is 20, equals, you got minus 4x plus 4x, which is, well, you have to add 4x to both sides, so it's going to give you 8x on this side. So you got 20 divided by 8 equals x. So x is equal to, they're both divisible by 4, 5 over 2, which is 2.5. The x value is 2.5. And to find the y value, you can say y is equal to 4 times 2.5 minus 7. So y is equal to, that's 10 minus 7, which is 3. So we can see the x value is 2.5 and the y value is 3. So we get to the same answer again using some sort of algebraic method as well. So you can use the same concept that we're using completing the square, thinking about the fact that this can never ever be negative. So the lowest value of this expression is going to be when it's 0, which is going to be 2 times 0 plus 3, which is 3 for the y value. And what makes this 0 is when x is equal to negative 2.5, when x is 2.5, you're going to have 2 times 2.5, which is 5, minus 5, which is 0. So we've worked it out. That's by far the easiest way of doing it. Okay, so that's the way that I would probably use. Just, show these steps over here. And we would have everything separate here. Yeah, there we are. I would have done something like that, shown those steps over here, and I would have got my answer. Therefore, the coordinates of P are 2.53. Okay, so that's a long first answer, but it's because I showed you the different ways of doing it. But this is by far the easiest way of doing it. Now, part B, it says solve the equation f of x equals 3x minus 2. Okay, 3x minus 2 would be in a line which goes through minus 2 on the y-axis, and it has a gradient of 3. So it's going to be having a gradient which is shallower than this gradient. Okay, so let's see where it passes through. F of x equals 3x minus 2. So it's going to go through minus 2, and it's also going to go through the point of y equals 3x minus 2. When x is 0, y is minus 2. When y is 0, you're going to have x. When y is 0, you're going to have x is 2/3. So it's going to go through a point somewhere over here. So it'll probably look something like this. It's shallower than that line. It's going to look something like this. Okay, so it's going to probably cut the line in 2 places. That's what I'm imagining. And this is 2/3, and this is minus 2. Okay, so this is y equals 3x minus 2. This has a gradient of 4. This has a gradient of 3, so it's shallower. Now, I can see that it's going to meet this curve in 2 places, these 2 places here. And this place is at the point where y equals minus 4x plus 13. So what I would have done in this question, if I had used the other method of what I did use, the vertex method, where I considered it in this form for part A. For part B, I would have done exactly the same thing I've done now, which is I would have found the positive and negative arguments of the graph to work out which branch of the graph has which equation. And then I would have said, okay, this point here where it meets the graph, I'm going to call it point A, and I'll call this point B. I can say at point A is where y equals 3x minus 2 meets y equals minus 4x plus 13. So I can say 3x minus 2, make that a bit neater. So I can say over here that 3x minus 2 is equal to, and we're going to have the minus 4x plus 13. So that's the point. That's the point that I've called A. And I've called the other point B, okay, where 3x minus 2 is equal to 4x minus 7. So 3x minus 2 is equal to the positive argument of the graph, which is 4x minus 7. So if I solve this, this is going to give me 7x is equal to 15. So x is equal to 15 over 2. So that's the solution from that part. Just asking for the solution means just the x values. And here I'm going to have minus 2 plus 7 equals 4x minus 3x, which is x. So x is going to be 7 minus 2, which is 5. So those are the 2 coordinates So this is 15 over 2, okay, which is going to be 7.5, and this is 5. So we have 5 and 7.5. Okay. Let's have 15 over 7. What am I talking about? 15 over 7. That's not right. I thought there was something strange there. That's 15 over 7. Sorry about that, guys. Okay. And how did I know I was wrong? I mean, I made a stupid mistake there, which is anyone can do, but I knew I was wrong for a reason. So, because I knew that this value, 15 over 7, is going to be 2 and 1/7, right? So what I had before was 15 over 2, which is 7.5, and I've got x equals 5. So I know for sure that if this is 2.5 and the values are 5 and 7.5, that's not going to be true. One of the values has to be less than x equals 2.5. So that's why I knew that there's something wrong, something was amiss here, okay, because it has to be, one of them has to be less than 2.5. Okay, so this is where I thought, okay, there's something wrong somewhere. So then I noticed I did 15 divided by 2 instead of 15 divided by 7. Okay, so it's very important that you do think about your answers being sensible, and that's one way of, you know, looking or finding errors. Everyone can make a stupid mistake. It's very, you know, we're all humans. But, you know, if you have this idea of just thinking if your answer is sensible. So what I did, I looked back up here and I saw that there has to be a value that's less than 2.5 where they intersect. Okay, and it can't be, you know, that both of them are on this side. It's not possible. So therefore, I didn't check to see if I made a silly mistake, and I did, which was here. I put 15 over 2 instead of 15 over 7. So here we have the two answers. X equals 2 and 1/7, or 15. That's 15 over 7, or x equals 5. Those are the two solutions for this. The solutions of this equation. That's part B, and now part C. It says, given that the equation f of x equals kx plus 2, where k is a constant, has exactly 2 roots, find the range of values of k. Okay, so now kx plus 2 means it crosses the x-axis at 2. Now this is 3, so it's going to be a bit below here. This is, remember, 3. This is 2.53. And if it has exactly 2 roots, that means that the line, okay, so this thing can have a gradient that changes. K is a gradient. You see, this is y equals mx plus c. Y equals mx plus c. So the thing that's fixed, the k is the gradient. So the gradient can vary, okay, but we want to know how it can vary so that there's going to be exactly 2 roots. Okay, so exactly 2 roots means it's going to cut the function f in exactly 2 places. Exactly 2 places. Okay, so what we can do here, let me just make this a bit thinner. Okay, so what we can do here is we can think about this line. Now this line is going to go through 2 here, and it's going to have a gradient that varies like this. Okay, this line here will continue on forever. This line here will continue on forever. On this side. Whoops. Okay, it's going to continue on this side because it does continue like that because it's a continuous function, and there's nothing that tells us to stop drawing this particular line on this side. Okay, so this continues on forever this way, but on this side it stops here because if you look back in the equation that we had, it says that x is greater than 0. So I'm going to take this equation actually, put it on the other side so we can see it, including this. So it says x is greater than or equal to 0, meaning that this function starts from x equals 0. So there's no negative part of this function at all. Okay, so this function here, the original function which they've called f of x, as you can see, it starts from x is equal to 0. So this line that we've drawn here, okay, its gradient can vary. So it can be like this. Now, as long as it's like this, it's going to have exactly this. It's going to have 2 points that it meets. So at the point P, when its gradient is like this, okay, when its gradient is like this, it's going to hit this curve in one place when it touches at the vertex. But anything slightly above that, there's going to be two solutions. There'll be two routes because they'll cut it in two places. That's what it means by two routes. There'll be two places where it hits that curve, that line. And it'll continue having two routes. It will continue having two routes, even, you know, as you go further up, because remember, this continues on forever on this side. So it's going to continue cut it in two places. It will continue cutting in two places. It will still cut it in two places. All right, somewhere further up there. I can't actually draw it on the graph right now because it's going to be so far up. Okay, but eventually it's going to become parallel to this line. Once it becomes parallel to this line, it will no longer be able to, it will no longer meet it again. It will only have one route. So at the point where it becomes parallel, it's going to have just one route. So just before it becomes parallel, it's going to have two routes. Okay, because it will meet it eventually somewhere further up here, which is not on the graph. We can't show it, and it will meet. It will meet it again, so that it's going to meet at two places, and at this point P, one place. So anything above any gradient, when the gradient of this line is anything above the gradient now, it'll have two routes, and it'll continue having two routes until its gradient becomes the same as the gradient of this negative argument of the curve. And remember, this was y equals minus 4x plus 7. Okay, so we need to find the gradient of the line when it is in this position first. This is like the one limit. Okay, so the gradient between the points 0, 2 and 2.53. So the gradient is going to be 3 minus 2, which is 1 over 2.5 minus 0, which is 2.5. So that's going to be 1 over 5 over 2, which is 2/5. So this gradient is 2/5. And the gradient of this line here, we can say the gradient of this line is minus 4. So when the gradient of our line, which is called k in this question, okay, k is the gradient of the line, is greater than 2/5, greater than 2/5, and less than 4, there will be two routes, because when it's equal to 2/5, there's one route only. When it's less than 2/5, there's no routes. When it's equal to 2/5, there's going to be one route. When it's greater than 2/5, when the gradient of this line is greater than 2/5, like over here, there's going to be two routes, and there will continue being two routes until this line is parallel to the line there, in which case until the gradient equals 4. So everywhere between those there will be two routes. Okay, and you know, it will have, after that it'll just have one route and one route and one route until it becomes a vertical line. Then over there it's going to have no routes. So basically between this point and the point that they're parallel, there will be exactly two routes. Okay, not including the gradient when it's at that point, and not including the gradient when it's equal to 4, everything between them. So I hope that was understood and clear. So that's the end of this question number 6. I think that was the end of it, yes. So thank you for watching, and I'm going to have a playlist with other questions from this paper placed in the playlist that you can find from this link that should appear somewhere in this section. Questions from this topic of functions and graphs from P3 you'll find in this playlist over here. You can subscribe to the channel from this link here, and I will have a link, a card showing, should have been showing from the beginning of the video at certain points, taking to another past paper from P3, maybe a specimen paper or something like that. So thank you for watching, and I hope to see you again soon.